This is a review of Cartesian coordinates, polar coordinates, and normal tangential coordinates. Alrighty? Now, this is going to take some drawing skill on my part, so bear with me if I seem to be laboring over the figures, because what I'll tell you right up front, this is a situation where, let me be clear, I am not talking about different situations. I'm going to tell you the same story from 3 different perspectives, all right? Either in 2D, either in the plane or in 3D, everything that I'm going to tell you here applies equally. I'm going to do it in 2D for convenience, but trust me, it applies in 3D just as well, all right? So we have is a path, also known as a trajectory, through which a particle is proceeding as a function of time. Fair enough? And this is described thusly. All right, that's called the position by a vector. Okay, typically, I'll show you in a minute, different forms, okay, but this is a vector that describes the position of a particle that follows a path as time proceeds. If we take the derivative of that, we're going to call that the velocity. Okay, and take my word for it, the velocity is by definition always tangent to the curve. And if we differentiate that further, conventional time derivative, we get something called the acceleration. All righty? So there's the 3 critters: position, velocity, and acceleration. And we're going to look at this 8 ways from Sunday. All righty? Very first one, simplest, is in Cartesian coordinates, such as are depicted here. This becomes dirt simple. The position vector is written simply like this. Where these are the unit vectors I spoke of before. The x and the y axis respectively have unit vectors. And what we have here is simply the x and y component of the position. Excuse me, now I got to slow down here lest I make the position components are simply x and y. Is that clear? All right. The x and y are simply the Cartesian components of the vector from the origin to the point in question. That makes the velocity exceedingly simple to compute. You simply take the time derivative of those components. And ditto with the acceleration. Alrighty, that's the easy one. And let me point out, and I'm going to draw these in 2 steps, or I'm going to have different diagrams here just so I don't make it so messy you can't see it. So once again, here's the position. Only this time, this is the path. And again, if you, let me put this here. Okay, can everybody see this? Now let me put the velocity on this guy. All right, now once again, this is to the best of my ability to draw exactly that same figure. That is my intention to draw I'm talking about the exact same thing. All righty? What we're going to do is we're going to simply look at it from a different perspective. We're going to define polar coordinates thusly. Okay? We're going to define two new unit vectors. Okay? I'm going to call this one u sub r. I'm going to call this one u sub theta. Now, I hope it's clear to people. There's one of them, and here's the other. Okay, u sub r and u sub theta. What these do are, these define basically two new directions. The Cartesian axes defined the simple directions, this way and that, horizontal and vertical. All right, this one's a little squirrelier. This direction is in the direction of the vector r. All right, so it's called u sub r hat, and perpendicular to it is u sub theta hat, and we do that as well for the acceleration. This is u sub r hat, and this is u sub theta hat. Okay, and this is, once again, this is x, and this is y. And these are our unit vectors now. Okay, now here is kind of key point number one. Now, this becomes, if you will, the position now becomes simply a scalar length times the first of the unit vector, u sub r, all righty? The velocity becomes r dot u sub r theta, hat rather, plus r theta dot. Okay, now does everybody appreciate that, what we're doing here? And so what this is, now, that is this one right in here is, let me move this. And what this is, this component right here, is r theta dot. Okay? Everybody appreciate that? And over here, let me write it down here. As if you had just differentiated it, you'll see this is all right, so there's the other one. Did I square those? I box those? Pardon me for a second. That's pretty good, two at a time. The Cartesian form and the polar form. Okay, any questions about this? I'm assuming you guys have had, this is not your first exposure to polar coordinates, correct? Is there anyone for whom this is brand new? Fabulous. Because we're going to use this a lot, okay? Because the situation is that different problems lend themselves to solution if you choose different coordinate systems, all right? Let me just do the last one, NT. And I want to point out that on the website, on the very first items called review videos or review materials, all right? And one of those is on this. If it's been a while since you've done it, or you never saw it derived, I strongly encourage you to go through that video, which will show you where these came from. All righty? Yes, ma'am. Question came from, there you are, your name?
Marion.
Marion.
That is theta dot squared, correct? For acceleration, the first
Right
term.
here? This one here?
Yeah.
I believe so. Yeah, hang on a second.
Just clarifying.
Oh, yeah. Yeah, this one here, yeah, it's r double dot minus r theta dot squared. Okay, yeah, sorry about that. Moving a little too fast. Okay, now the last one is a so-called normal tangential coordinates, and it looks like this. Once again, there is a path. Once again, I'm trying to draw exactly the same situation. So there's the path, there's the velocity, and somewhere out in here is the acceleration. Now this one is different yet. There is still a third choice of unit vectors. This one unit vector is in the direction of the velocity, just because I said so, okay? We're just choosing a direction from which to view the velocity and the acceleration. The direction in question is wherever the velocity is heading, all right? That's what unit vector number one is, and the other one is, not surprisingly, 90 degrees away. This one going in this direction is called u sub n. The term reference being tangential to the path or normal to the path. Make sense? This is particularly useful for trajectories of flying objects or race cars or something of that sort. Anyway, then the formulas become this. It's simply v times the unit vector in the tangential direction, and the other is okay. Now let me just say, there's some things that aren't stated here. Basically, at this point, more than you want to know, if you took a point just before and just after, plus and minus delta t, and you fit a circle to those 3 points, and then you took the limit as those points came together, there would be a circle. It actually has a name. Anybody know what it is? It's a name. Say again? No, don't hear it. Anyway, it's not one you'll guess. It's called the osculating circle. All right? Any Latin buffs here? Anybody know what osculate, or the root is? It means to kiss. Okay? It's a circle tangent to the curve that has the same radius of curvature. And you're familiar with, I don't have that formula for curvature, but that's what this is. This is rho. Okay, that is the radius of curvature. Okay, and so the component of the acceleration in this direction is v squared over rho, All right, you're familiar with that. And then the component in this direction is simply the rate at which the velocity is increasing its magnitude. Okay, questions, comments?